Stand beside nuclear reactor core. Uranium fuel pellets, small as gummy bears, generate heat exceeding 5,000 degrees. The only material containing this inferno is zirconium, metal so rare that global annual production barely reaches 1 million pounds. Every American nuclear reactor depends on zirconium tubes called cladding, preventing radioactive fuel from contaminating cooling water. One facility in Albany, Oregon, ATI Wah Chang, produces every pound of reactor-grade zirconium in the Western Hemisphere. This single plant supplies 93 American reactors plus facilities worldwide. How does obscure metal become sole barrier between controlled reaction and catastrophic meltdown? Why does one Oregon factory hold monopoly on material critical to national energy security? Stay with us. You'll witness chemistry so violent it requires titanium-lined vessels and discover zirconium's terrifying secret? The metal protecting us from radiation is itself pyrophoric, burning spontaneously if exposed incorrectly. ATI Wah Chang sprawls across 400 acres along Willamette River, industrial complex operating since 1956. The main processing building stretches quarter-mile, containing chemical reactors, furnaces, and rolling mills, producing materials no other Western facility can manufacture. Security rivals military installations, armed guards, badge checkpoints, cameras monitoring every corner. This isn't paranoia. The knowledge and capability concentrated here represent strategic asset. Lose Wah Chang and America's nuclear fleet stops operating within 18 months. Watch the receiving dock. Trucks arrive from Australian mines carrying zircon sand, ZrSiO4, dull brown mineral resembling beach sand. This sand contains 49% zirconium oxide mixed with silicon dioxide. 600 workers across 3 shifts process 12 million pounds annually. The facility never stops. Nuclear reactors don't wait. Fuel assemblies require replacement on precise schedules. Delay means reactor shutdown, electricity shortages, economic losses measured in billions. Wah Chang operates under pressure few industries experience. Zero tolerance for failure, absolute requirement for perfection. The chlorination process begins zirconium extraction through chemistry, so aggressive it destroys ordinary equipment. Zircon sand gets mixed with petroleum coke and fed into fluidized bed reactors operating at 2,000 degrees. Chlorine gas, deadly poison in World War I trenches, bubbles through at carefully controlled rates. The chlorine attacks zircon, forming zirconium, tetrachloride gas plus silicon tetrachloride as byproduct. This reaction is viciously exothermic, releases heat that would melt steel vessels. The reactors use water-cooled jackets maintaining precise temperature control. Too hot, the reaction runaway destroys equipment. Too cool, conversion stalls wasting materials worth thousands per batch. Operators monitor from control rooms behind thick glass. The chlorine concentration remains lethal. One breath kills instantly. Safety systems include automatic shutdown triggers, emergency ventilation, and decontamination showers. Working chlorination means accepting proximity to industrial-scale poison production. One valve failure, one seal breach, one monitoring error equals disaster. Magnesium reduction transforms zirconium tetrachloride into metallic zirconium through pyrotechnic chemistry. The tetrachloride gas, cooled and purified, enters massive steel reactors containing molten magnesium, heated to 1,600 degrees. When gases meet, violent reaction produces zirconium sponge plus magnesium chloride salt. The heat release is so intense that reactors glow red despite foot-thick walls. The reduction happens batch-wise in vessels called retorts, each containing 8,000 pounds of magnesium. The reaction takes 48 hours, temperature and pressure monitored continuously. As zirconium forms, it appears as porous metallic sponge-coating reactor interior. After cooling takes 3 days, workers jackhammer the sponge free. Brutal process, but no alternative exists. The sponge, brittle and reactive, gets crushed and graded by particle size. This powder will become reactor cladding, but first requires purification beyond anything else in metallurgy. Electron beam melting achieves purity unmatched in industrial processing. The zirconium sponge, still containing trace magnesium chloride and other impurities, gets compacted into electrodes and loaded into vacuum furnaces. These furnaces evacuate to 0.0001 atmospheres, better vacuum than low Earth orbit. An electron beam, essentially lightning bolt focused through magnetic lenses, melts the electrode tip at 11,000 degrees. Watch through lead glass viewport as electron beam strikes. The zirconium glows blue-white, temperature exceeding sun's surface. Molten droplets fall into water-cooled copper mold, solidifying as ingot. Impurities vaporize in vacuum. Magnesium, iron, carbon, everything except zirconium boils away. The process repeats 3 times, triple electron beam melting, achieving purity of 99.995%. For nuclear applications, this isn't perfectionism, it's survival. Impurities in cladding absorb neutrons, poisoning reactor, reducing efficiency, potentially causing fuel failure. Hot extrusion transforms solid ingot into hollow tubes through precision violence. The zirconium ingot, reheated to 1,400 degrees, becomes workable but not liquid. Hydraulic press generating 8,000 tons, force drives ingot through die, creating tube blank, solid cylinder with center hole. The metal flows like frozen honey under impossible pressure, crystal structure reforming around mandrel. The extrusion press shakes the building, low-frequency vibration felt in chest rather than heard. Workers coordinate via hand signals, verbal communication impossible over mechanical thunder. The tube blank exits glowing orange, immediately transferred to beta quench, rapid cooling that locks in desired microstructure. Zirconium exists in 2 crystal forms, alpha below 1,500 degrees, beta above. The beta structure, rapidly cooled, provides optimal combination of strength and neutron transparency. Getting this wrong makes material useless for nuclear applications. Cold pilgering reduces tube dimensions through iterative working. The process, invented in medieval Europe for making gun barrels, remains unsurpassed for precision tube manufacture. Tube blank gets placed over mandrel and fed through dies that rotate and reciprocate simultaneously. Each pass reduces diameter and wall thickness while increasing length. The tube grows like taffy being pulled. 28 passes transform 2-foot blank into 40-foot tube with walls 0.023 inches thick, dimension controlled to millions. The cold working strain hardens zirconium, requiring intermediate annealing at 1,000 degrees to restore ductility. The tubes undergo dimensional inspection using laser micrometers scanning entire surface. Every measurement gets recorded, complete metrology traceability from ingot through final product. Nuclear regulators demand this documentation. One tube failure in reactor means investigation examining every manufacturing detail. ATI Wah Chang began as Oregon Metallurgical Corporation in 1956, founded specifically to produce zirconium for nuclear industry. The facility pioneered commercial-scale electron beam melting, magnesium reduction, and vacuum processing techniques now standard worldwide. During Cold War, Wah Chang supplied zirconium for nuclear submarines. Nautilus, first nuclear sub, used Wah Chang cladding. In 2004, Allegheny Technologies acquired the facility, integrating into aerospace and defense supply chain. The Albany plant remains only Western source for reactor-grade zirconium. Russia and China produce zirconium domestically, but Western utilities won't use it. Quality concerns plus geopolitical risk. France attempted domestic production, failed economics. Japan imports from Wah Chang. The Oregon facility holds monopoly not through market manipulation, but through accumulation of irreplaceable knowledge and infrastructure impossible to replicate. Environmental impact carries nuclear stigma despite reality. Producing zirconium generates chlorine byproducts requiring neutralization, plus magnesium chloride salt requiring disposal. The facility maintains zero discharge to Willamette River. All water gets treated, recycled, or disposed through licensed facilities. Air emissions meet EPA standards but include trace chlorine and hydrochloric acid, yet zirconium enables nuclear power, cleanest large-scale electricity generation. Each reactor Wah Chang supplies prevents emission of 4 million tons. CO2 annually versus coal equivalent. Here's the secret we promised. Zirconium's nuclear dominance stems from neutron transparency combined with corrosion resistance. Most metals absorb neutrons, poisoning reaction. Zirconium is essentially transparent to neutrons while withstanding high-temperature water corrosion for years. But zirconium has dark side, it's pyrophoric. Fine zirconium powder burns spontaneously in air. During Chernobyl and Fukushima meltdowns, zirconium cladding reacted with steam, producing hydrogen that exploded violently. The metal protecting us from radiation can amplify disaster. From Oregon riverbank to reactor cores worldwide, the transformation completes. ATI Wah Chang represents capability concentration, decades of knowledge, billions in specialized equipment, and workforce expertise that cannot be bought or replicated quickly. America's energy independence depends on this one facility continuing operation. That electricity powering your home might flow from reactor using Wah Chang cladding. The nuclear submarine patrolling oceans depends on tubes made in Albany. We've concentrated strategic capability in single point of failure because no economic incentive exists for redundancy. Wah Chang doesn't just make zirconium, it holds monopoly on material nuclear civilization cannot function without.
Imagine a metal that's lighter than steel, stronger than aluminium, and can withstand temperatures at which other materials simply burn up. A metal used to build aircraft that conquer space and implants that serve people for a lifetime. Sounds like science fiction? But this is titanium, one of the most mysterious metals on Earth. It starts with tiny grains of ilmenite and rutile and ends up as parts for supersonic jets and spacecraft. But few people know. Behind the gleam of titanium lies a manufacturing secret so dangerous and energy intensive that it's rarely spoken of. If you watch till the end, you'll learn something that will forever change your perception of this metal. The story of titanium production begins in the late 18th century when, in 1791, a British clergyman and amateur mineralogist named William Gregor discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, the pure metal was first successfully isolated only in 1825 by the Swedish chemist Berzelius, though at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and the real breakthrough came in 1925 when Dutch scientists Van Arkel and de Boer developed a method for producing high-purity titanium, paving the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the USA, where the metal became indispensable in aviation, the space industry, and military applications. The production of titanium starts with the mining of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in placer or lode deposits and are widespread across the globe, particularly in Australia, Canada, China, Norway, and South Africa. After mining, the ore undergoes a complex multi-stage processing. First, it is enriched, separating the titanium minerals from the waste rock to obtain ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, the titanium tetrachloride is reduced with magnesium or sodium in special reactors at high temperatures in an inert atmosphere, producing titanium sponge, a porous metallic powder. This titanium sponge is then pressed, melted, and cast to obtain ingots or billets for further processing. The production of titanium is energy-intensive and expensive due to the complexity of the technological processes and the need to work in high-purity conditions. The main industrial method for producing titanium is the Kroll process, which remains the global standard. It involves the chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, allowing for the production of high-quality metal for aviation, space technology, medicine, and other industries. Thus, titanium production begins with the mining of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex, multi-step technological process that begins with the extraction and preparation of titanium-bearing raw materials, mainly ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. To do this, the titanium ore concentrates are chlorinated in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and chlorine gas react with the raw material to form titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation to obtain high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at high temperature. The result is titanium sponge, a porous metallic powder containing impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the titanium sponge is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used to produce alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is titanium sponge. It looks nothing like a regular metal bar, but more like a piece of metallic sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First and foremost, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that enhance its properties. To obtain an alloy, alloying elements are added to the molten titanium, most often aluminium, vanadium, molybdenum, iron, or niobium. These additives change the metal's structure, increasing its strength, heat resistance, corrosion resistance, and improving its workability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, after which it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more malleable and are passed through special rollers. Rolling allows for reducing the metal's thickness, giving it the desired shape and size, as well as improving its structure and mechanical properties. The result is various types of rolled products: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. From these rolled products, sheet metal is made, thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are distinguished by their high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and its alloys are used. These can include mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometries that are impossible to produce with traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are required. Furthermore, to enhance their performance characteristics, titanium products can undergo heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used for 15% of the weight of a modern passenger aircraft, significantly reducing its overall weight and increasing fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability.
Check your smartphone battery. It contains roughly 0.01 ounces of cobalt. Your laptop holds 10 times more. Electric vehicles require 30 pounds per battery pack. This bluish-gray metal, rarer than platinum, enables rechargeable batteries powering modern civilization. Global demand exceeds 200,000 tons annually, growing 20% yearly. One nation controls 70% of supply, Democratic Republic of Congo, where cobalt mining represents technological progress built on human suffering. How does obscure metal buried in African soil become indispensable to iPhones and Teslas? Why can't battery manufacturers escape dependency on ethically compromised supply chains? Stay with us. You'll witness industrial-scale extraction reshaping Congo's landscape and discover cobalt's devastating secret. The green energy revolution runs on metal mined by children. Kolwezi district in Congo's Katanga province contains world's richest cobalt deposits, ore bodies stretching 40 miles containing 8 million tons of recoverable cobalt. Glencore's Mutanda mine dominates the landscape. Open pit 2 miles across, descending 1,000 feet. Giant haul trucks, each carrying 400 tons, create spiral roads visible from space. This single operation produces 25,000 tons of cobalt annually, enough for 5 million electric vehicle batteries. But industrial mining tells only half the story. Surrounding the massive pit, tens of thousands of artisanal miners, cruciers, dig by hand. They tunnel through unstable soil with shovels and pickaxes, extracting ore from shallow pits and abandoned mine shafts. No safety equipment, no ventilation. Children as young as 7 work alongside adults, earning $2 daily. The contrast is staggering. Billion-dollar machinery operates next to subsistence miners dying for scraps. This is cobalt's duality, cutting-edge technology enabled by Stone Age extraction. The ore, heterogenite and kerolite, contains 3 to 8% cobalt, always mixed with copper. Massive crushers reduce ore to gravel. Ball mills grind further, creating powder fine as flour. The grinding buildings operate continuously, deafening roar as steel balls pulverize rock. Each ton processed yields 60 pounds of cobalt and 300 pounds of copper. Cobalt is byproduct, making economics complicated. Flotation separation begins in enormous tanks containing chemical froth. Copper sulfides attach to bubbles, floating to surface for collection. Cobalt remains in solution, requiring different chemistry. The process generates massive waste. For every ton of cobalt extracted, 200 tons of tailings remain. These waste ponds, acidic and toxic, stretch for miles. The environmental damage is permanent. Soil contaminated for centuries, groundwater poisoned indefinitely. But demand doesn't care about consequences. Battery manufacturers need cobalt, whatever the cost. Cobalt concentrate undergoes hydrometallurgical processing, chemical extraction replacing traditional smelting. The concentrate dissolves in sulfuric acid at 180 degrees. Copper precipitates first through pH adjustment, Then cobalt gets separated from nickel and manganese through solvent extraction, organic chemicals selectively binding cobalt ions. The chemistry is precise, requiring exact pH, temperature, and reagent concentrations. The result is cobalt sulfate solution, pink liquid containing 20% cobalt. This solution ships to refineries, mostly in China, where final purification occurs. Electrolysis deposits pure cobalt metal onto cathodes, sheets of cobalt growing atom by atom from solution. The metal emerges silver pink, hard and brittle, but most cobalt never becomes metal. It stays as cobalt sulfate or cobalt oxide powder, the forms battery manufacturers require. The entire supply chain funnels through Chinese refineries, controlling 80% of global processing capacity. Battery-grade cobalt demands extreme purity, 99.8% minimum. Impurities like iron, nickel, calcium cause battery degradation. Quality control happens through mass spectrometry analyzing samples to parts per billion accuracy. Rejected batches get reprocessed. Nothing wastes when material costs $60,000 per ton. The powder gets carefully packaged in sealed drums, each containing 500 pounds. These drums travel to battery manufacturers, LG Chem, CATL, Panasonic, the companies powering Tesla, Apple, Samsung. The cobalt combines with lithium and nickel in precisely calibrated ratios. Lithium provides energy density. Nickel adds capacity. Cobalt delivers stability, preventing thermal runaway, the catastrophic failure causing batteries to explode. Manufacturers desperately seek cobalt-free alternatives. None work as well. The chemistry is frustratingly specific. Inside battery factories, cobalt powder mixes with lithium and nickel oxides, creating cathode material. This mixture gets coated onto aluminum foil in layers thinner than human hair. The precision is absolute. Coating must be uniform within 2% variation. Any inconsistency creates hotspots during charging, potentially causing fire. The coated foil, along with graphite-coated copper anode and separator membrane, gets wound into cylindrical cells or stacked as prismatic cells. These cells fill with electrolyte, lithium salt dissolved in organic solvents. The electrolyte allows lithium-ion movement between cathode and anode during charging and discharging. Each cell undergoes formation cycles, controlled charging that activates materials and identifies defects. Failed cells get disassembled, materials recycled. The waste is too valuable to discard. Battery recycling could solve cobalt shortage, but currently only 5% gets recycled. The process is challenging. Batteries contain diverse chemistries mixed with plastics and electronics. Shredding risks fires from residual charge, but economic incentive grows. Recycled cobalt costs 40% less than mined material. Hydrometallurgical recycling dissolves batteries in acid, separating metals through selective precipitation. The recovered cobalt, lithium, and nickel return to battery production with identical performance to virgin materials. The circular economy remains theoretical. Most batteries end up in landfills or incinerated. Cobalt lost forever. Companies like Redwood Materials and Li-Cycle are building recycling infrastructure, but scale remains insufficient. By 2030, experts predict recycled cobalt could supply 30% of demand. Until then, Congo's mines run continuously, extraction accelerating despite consequences. Cobalt derives its name from German kobold, goblin, because medieval miners blamed goblins when cobalt ore poisoned them during silver extraction. For centuries, cobalt's only value was blue pigment in pottery and glass. Everything changed when John Goodenough invented lithium-ion battery in 1980. His cobalt oxide cathode enabled rechargeable batteries light enough for portable electronics. Sony commercialized the technology in 1991, launching the mobile revolution. Initially, cobalt demand remained modest. Cameras, laptops, phones use small batteries. Then electric vehicles emerged. A single Tesla Model S contains 24 pounds of cobalt, equivalent to 1,000 smartphones. As EV adoption accelerates, cobalt consumption grows exponentially. By 2030, transportation will consume 60% of global cobalt supply. The metal that poisoned medieval miners now powers humanity's energy transition. Irony lost on nobody. Carbon emissions perspective shows paradox. electric vehicles reduce emissions 80% versus gasoline cars over life cycle. But mining cobalt generates massive environmental damage plus humanitarian crisis. Children in Congo work illegal mines, exposed to dust causing respiratory disease, digging tunnels that collapse regularly, earning subsistence wages while battery companies generate billions. Amnesty International documented children as young as 6 mining cobalt sold to major tech companies. The supply chain is deliberately opaque, or changes hands multiple times before reaching refineries, obscuring origins. Here's the secret we promised. The green energy revolution cannot exist without ethically compromised cobalt. Every Tesla, every iPhone, and every laptop depends on metal extracted under conditions violating international labor laws. Battery manufacturers know this. They issue statements promising ethical sourcing while buying through intermediaries, providing plausible deniability. The truth is uncomfortable. Transitioning away from fossil fuels requires accepting different moral compromises. We've replaced oil fields with cobalt mines, exchanging one exploitation for another. From Congo's pits to Silicon Valley's gadgets, the transformation completes. We've created technology liberating us from combustion engines while enslaving miners and supply chains we refuse to acknowledge. That electric vehicle representing environmental consciousness contains metal mined by children. The battery in your pocket enabling instant global communication required someone else's suffering to exist. Progress always demands sacrifice. We've just decided others should make it. Cobalt doesn't just power devices, it exposes civilization's willingness to ignore atrocity for convenience. We know the cost. We pay it anyway.
Every year, over 40 million new gadgets hit the market, but almost nobody knows about the metal that makes them actually work. Why can a tiny element buried deep underground literally launch an entire civilization, from the Bronze Age to modern electronics? And what do ancient swords, tin cans, and your smartphone have in common? In this video, we're uncovering the secret of tin, the metal that built the past, runs the present, and hides a fact you've definitely never heard before. Stick around until the end. That's where the real mystery reveals itself. Tin isn't just some new trend. This is a metal with a deep-rooted history spanning thousands of years. Its discovery sparked a genuine revolution that forever transformed the course of human civilization, launching what we call the Bronze Age. Picture this. Ancient craftsmen learned to extract copper and forge tools from it. But copper was soft. Then, whether by accident or experimentation, they discovered something remarkable. If you added a little bit of another then unknown metal to molten copper, tin, the alloy became incredibly strong, hard, easier to cast, and held a sharper edge. That metal was tin. The copper-tin alloy became known as bronze. Bronze swords, shields, tools, jewelry, all of this suddenly became accessible, giving ancient civilizations a massive advantage. It was a true technological leap that transformed warfare, agriculture, and art. Tin became so valuable that real battles were fought over its deposits, and trade routes to tin mines, like those in Cornwall, Britain, were incredibly important. Over the centuries, tin stayed valuable. It was used as a coating for other metals to protect them from corrosion. For example, tin plate, a thin sheet of steel coated with tin, which was used to make cans. It was also used to make soft solders that joined metals together, and in the production of mirrors, and even to create organ pipes and coins. But its true renaissance came in the 20th century with the rise of electronics. Over 50% of all global tin consumption goes to this industry. Solder. That's its main job. Your computer, smartphone, TV, inside them, thousands of electrical components are connected together. These connections are made using solder, which is usually an alloy of tin with other metals, like lead in the past, now mostly with copper, silver, or nickel. Tin is perfect for solder because it has a relatively low melting point, which makes it easy to melt and form connections without damaging sensitive electronic components. Tin also wets metals, meaning it easily flows across the surface, creating a strong electrical and mechanical bond. It's got great electrical conductivity too, and it's corrosion resistant. Modern electronics use what's called lead-free solder, which is a huge step forward for the environment. Tin is the main component in these alloys. Without reliable soldered connections, the entire complex architecture of microchips would simply fall apart, and your gadget would turn into a pile of useless parts. Tin is used to coat other metals, especially copper, on printed circuit boards. This protects the copper traces from oxidation and makes the soldering process easier. It's also used to coat connectors, which improves their electrical conductivity and corrosion resistance. Tin isn't a super common element in the Earth's crust. Its primary mineral is cassiterite, basically tin oxide. It's a pretty dense mineral that's often found in placer deposits, meaning you can extract it from river sediments or ancient coastlines. Over 70% of the world's tin production is concentrated in 4 countries across Southeast Asia and South America: China, Indonesia, Myanmar, and Peru. This makes the tin market highly sensitive to political and economic events in these regions. Tin mining begins with the exploration phase. Geologists, armed with modern technology, conduct surveys, drilling, and analysis of soil and rock samples to find locations where cassiterite concentrations are high enough for economically viable extraction. Once a deposit is identified, development begins, which can follow 2 main paths depending on the type of deposit. The first and most common method of tin mining is from placer deposits. Picture this. Over millions of years, cassiterite washed from bedrock by water and erosion accumulated in riverbeds, at the bottom of lakes, or on ancient seashores.
It settled like sand in what's called placer deposits. Extracting from these deposits is often way simpler than digging underground mines. Here, they use massive dredges, floating factories that scoop up tons of soil and gravel from the bottom of waterways, or they deploy hydraulic monitors, powerful jets of water under high pressure that blast away soil from riverbanks or hillsides containing cassiterite. The blasted rock then flows to primary processing, where gravity methods, exploiting density differences, separate the cassiterite from lighter waste rock. Think industrial-scale gold panning, only gigantic. The second method? Extracting from primary deposits, where cassiterite sits directly in solid rock. That's where traditional underground mines come in, same as mining any other metal. Miners drill tunnels and boreholes into the rock, use explosives to blast apart the ore vein, then loaders collect the ore and haul it to the surface. It's a more expensive and complex operation, requiring heavy-duty equipment and strict safety protocols. Once extracted, the ore, no matter where it came from, heads to a processing plant. First, it's crushed and ground into a very fine powder in mills to free the cassiterite crystals from the surrounding rock. Then various enrichment methods kick in. The first method, gravity separation. Since cassiterite is a pretty dense mineral, it gets separated from lighter minerals using water. This can happen in jigs, concentration tables, or spiral separators.
The second method is flotation. Sometimes, for further enrichment or to separate cassiterite from other minerals, flotation is used, where cassiterite selectively sticks to air bubbles and rises to the surface as foam. As a result of all these processes, a tin concentrate is obtained that already contains more than 50% cassiterite, or even more. This concentrate then goes to a metallurgical plant to produce pure metallic tin. Here, the concentrate, which is tin oxide, is mixed with coal, which acts as a reducing agent, and fluxes. Fluxes are substances that help separate impurities. This mixture is heated in special furnaces to high temperatures, typically around 2400 degrees Fahrenheit. At these temperatures, the carbon steals the oxygen from the tin oxide, releasing pure metallic tin, which melts and flows to the bottom of the furnace.
The molten crude tin still contains impurities from other metals, so it goes through another crucial stage, refining. This can be thermopurification, where the lead is heated to specific temperatures so other metals separate out or float to the surface. Or more often, electrolytic refining, which allows for extremely high tin purity. High purity means almost 100% in this case. Can you believe that? This is critically important, especially for the electronics industry, where even the tiniest impurities can affect conductivity and component reliability.
Without nickel, Tesla's electric vehicles wouldn't exist. Every year, over 3 million tons of this silvery metal get extracted from Earth's crust, 70% destined for stainless steel, 30% powering the battery revolution transforming transportation. Picture this. Inside every electric car battery, nickel accounts for up to 80% of cathode weight, storing the electrical energy making 500-mile ranges possible. How does rock buried 2 miles underground become the metal enabling carbon-free futures? How do ancient asteroid impacts create deposits worth billions? Stick around till the end. You'll discover why this metal, discovered in 1751, became overnight the most critical resource for climate solutions, and the shocking environmental price we pay for every kilowatt-hour stored. The story begins in Sudbury, Canada, ground zero for one of Earth's largest meteorite impacts. 2 billion years ago, a 6-mile-wide asteroid slammed into primordial crust with force equaling 6 billion Hiroshima bombs. That cataclysmic collision melted rock 60 miles deep, concentrating nickel-rich magma into deposits mining companies extract today. Standing at crater's edge feels like visiting Earth's wound that never healed. Modern mining descends through vertical shafts, plunging 7,000 feet, deeper than 6 Empire State Buildings stacked vertically. Massive cage elevators, traveling at speeds exceeding 30 miles per hour, drop miners into darkness in under 4 minutes. That's falling through bedrock older than complex life itself. Underground, temperatures reach 120 degrees Fahrenheit from Earth's geothermal heat, requiring industrial air conditioning, pumping cold air through 40-mile tunnel networks. Next comes extraction, where explosive specialists drill blast holes following nickel-bearing veins. Charges containing ammonium nitrate, industrial explosive used in quantities measured by tons, fracture solid rock with controlled violence. The deafening thunder from underground blasts shakes surface buildings miles away, rattling windows in synchronized waves every afternoon at precisely 4 o'clock shift change. Giant load haul dump machines, nicknamed LHDs and standing tall as double-decker buses, scoop 50 tons per bucket. Picture mechanical mastodons navigating tunnels barely wider than their frames. Operating in perpetual darkness illuminated only by headlamps, drivers maneuver 60-ton machines through labyrinths where wrong turns mean hours backtracking. Every shift, these machines transport 15,000 tons of ore, weight equivalent to 75 blue whales, through underground highways to crushing stations. Surface processing begins where jaw crushers, standing 4 stories tall with opening widths matching garage doors, pulverize boulders into gravel-sized chunks. With bone-rattling vibrations felt through steel-toed boots, hydraulic jaws generate crushing forces exceeding 15,000 pounds per square inch. Operators monitor crack propagation. Rocks splitting wrong create jams requiring dangerous manual intervention with jackhammers. Conveyor systems stretching 8 miles, longer than Central Park, transport crushed ore to grinding mills. Inside rotating drums 30 feet in diameter, 25-ton steel rods tumble with ore, creating grinding cacophony resembling continuous thunder. Processing 12,000 tons hourly, that's loading freight trains non-stop. This powder, finer than beach sand, flows to flotation cells, where chemicals separate nickel sulfides from waste rock using bubble physics. Nickel concentrate emerges containing 20% metal, ready for the real challenge: purification. Next comes roasting, a pyrometallurgical inferno where concentrate gets heated in massive kilns to 1,400 degrees Fahrenheit. At these temperatures, sulfur burns away as sulfur dioxide, leaving behind nickel oxide mixed with iron. Picture industrial-scale barbecuing where the meat is rock and smoke contains compounds requiring scrubbing before atmospheric release. The roasted material, now crumbly and porous like volcanic pumice, moves to smelting furnaces, where temperatures climb to 2,600 degrees Fahrenheit. Electric arc furnaces, consuming power equivalent to small cities, enough electricity to run 12,000 homes, melt oxide into liquid matte. This molten mixture, containing 60% nickel and 40% other metals, glows white-hot like captured starlight. Every 2 hours, furnaces tap this liquid fire into ladles holding 200 tons. The purification process intensifies with converting, where oxygen blasted through molten matte at supersonic speeds burns away remaining sulfur and iron. Massive Peirce-Smith converters, rotating horizontal cylinders 40 feet long, operate like blast furnaces lying sideways. Inside these rotating drums, chemical warfare occurs. Oxygen attacking sulfur bonds, creating temperatures hot enough to vaporize copper. This step is critical because timing determines purity. Blow too long, nickel oxidizes wastefully. Too short, impurities contaminate final product. Operators monitor color changes in flames shooting from converter mouths. Blue flames mean sulfur burning, yellow indicates iron removal, clear white signals nickel ready. That visual chemistry, unchanged for centuries, guides decisions affecting millions in product value. After converting, nickel matte achieves 78% purity, but battery manufacturers demand 99.9%. After converting, the real magic begins, electro-refining. Here, physics and chemistry converge in massive electrode halls housing thousands of cells. Impure nickel anodes, cast into plates weighing 300 pounds each, suspend in electrolyte baths containing nickel sulfate and sulfuric acid. Electric current flowing through these baths, think industrial-scale electroplating, dissolves nickel atoms from anodes, transporting them through liquid to deposit on pure nickel starter cathodes. Picture this: over 10 days, nickel migrates atom by atom across 6-inch gaps. Impurities like cobalt, copper, iron stay behind, falling as sludge to cell bottoms. This sludge, later processed separately, contains precious metals including platinum, gold, palladium, making waste worth more than many ores. Temperature control matters critically. Too hot, dendrites form, metal crystals bridging electrodes causing shorts. Too cold, deposition slows uneconomically. Electro-refining requires surgical precision in industrial setting. Computer systems monitor voltage, amperage, temperature across 15,000 individual cells simultaneously. Operators adjust current by milliamps. Modern refineries achieve nickel purity of 99.99%, only one impurity atom per 10,000. That's purity rivaling semiconductor-grade silicon. After 10 days, workers crane lift finished cathodes, now coated with 400-pound nickel deposits from baths. Mechanical strippers peel nickel from starter sheets like removing wallpaper. These pure nickel sheets, called cathodes, get melted into pellets for battery manufacturers, or alloyed with chromium and iron for stainless steel. The energy intensity staggers. Producing 1 ton of battery-grade nickel consumes 50 megawatt-hours, enough electricity to power average American homes for 60 days. This industry transformed radically in 15 years. Back in 2010, nickel prices averaged $7 per pound, used primarily for stainless steel. Battery applications consumed less than 5% of global production. That all changed when Elon Musk's Master Plan 2 announced Tesla's battery gigafactories in 2016. The breakthrough came when battery chemistry shifted from cobalt-heavy NCAs to nickel-rich NCMs, nickel, cobalt, manganese cathodes containing 80% nickel. Suddenly, every electric vehicle needed 110 pounds of nickel. Global demand exploded. Prices spiked to $9 per pound by 2022. Indonesia, containing 21% of world's reserves, transformed from minor player to dominant producer. Today, battery applications consume 43% of new nickel production. By 2035, International Energy Agency projects batteries will consume 75%, driven by 200 million electric vehicles requiring 23 million tons cumulatively. Carbon emissions drop by 18% when recycling nickel versus mining virgin ore, equivalent to removing 3 million cars annually. Industry saves over $22 billion yearly through recycling. Processing costs drop 31% because smelting scrap requires half the energy of complete ore processing. So here's the secret promised. Nickel is humanity's transition metal, literally bridging fossil fuel era to electric future. But here's the dark truth. Extracting nickel for just one EV battery produces 8 tons of CO2 emissions. That electric car carries invisible environmental debt, requiring 35,000 miles of driving before breaking even with efficient gasoline vehicles. The green revolution isn't free. It's an energy trade-off where extraction today enables emission reductions tomorrow. From asteroid impacts to electric highways, cycle completes. We're mining ancient cosmic collisions to power climate solutions. Nickel doesn't solve pollution, it relocates it, concentrates it, transforms it into manageable problem. That's not failure, that's engineering reality. Every solution creates new challenges. The question isn't whether mining nickel harms Earth, it does. The question is whether preventing catastrophic climate change justifies temporary scars.
Every year, the world cranks out over 100 million cubic meters of medium-density fiberboard. That's such a massive amount that you could build a road around the entire planet with it, every single year. Imagine this. What was once trash, sawdust, wood chips, and scrap paper, is now transformed into a material worth over $25 billion. China controls half of the entire volume, while Europe and the US add millions of cubic meters each year. But what's really going on behind the factory walls, where wood dust goes from being waste to perfectly smooth panels? If you stick around to the end, you'll learn a secret that's usually kept hidden. The foundation for medium-density fiberboard isn't whole logs, but what used to be considered rubbish: sawdust, wood chips, offcuts, and even old scrap paper. It's a triumph of smart resource use. These mountains of wood waste are brought to the plant and first get a thorough cleaning. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage the expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't for cleanliness. It's done to soften the lignin, the natural glue that holds the wood fibers together. Now comes the most important step, the one that separates medium-density fiberboard from its rougher cousin, particle board. The prepared, softened wood chips are fed into a machine called a defibrator, or refiner. Imagine 2 giant metal plates, like millstones, spinning towards each other at enormous speed. On their surfaces is a complex pattern of sharp ridges and grooves. The wood mass gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't shavings anymore. It's something like a fluffy, moist cotton, or wood flour. We've just deconstructed the wood down to its basic building blocks. Next, this fibrous mass needs to be dried. But it has to be done very quickly, before the fibers start to stick together. So, they're blown into a long, hot tube dryer. A stream of hot air picks up the fibers, and as they fly through this tube, all the excess moisture evaporates from them. And right here, while the fibers are still hot and flying in this whirlwind, the next key stage happens: resonation. A fine mist of a binding agent is sprayed into the airstream through special nozzles. This is urea resin, our glue. This mist envelops every tiny fiber, coating it with a thin, sticky film. It's a very efficient method that guarantees a perfectly even distribution of the glue. Now this resin-soaked, dry, and light as fluff mass is ready to become a board. It goes into a forming machine. The stream of fibers settles onto a wide, moving conveyor, forming a thick, fluffy, and perfectly uniform mat. Special rollers slightly compact it, and giant knives cut off pieces of the required length. It's already starting to look like a future board, but for now, it's just a thick, soft mattress of wood fluff. And now comes the climax: hot pressing. This fluffy mat rolls into a giant press. This can be either a multi-opening press that squeezes a whole stack of boards at once, or a continuous press that looks like giant moving tracks. And here, our mat is hit by two powerful forces at the same time. First, colossal pressure. The press plates squeeze our fluffy mattress with hundreds of tons of force, reducing its thickness several times and squeezing out all the air. The wood fibers are pressed tightly against each other, forming an incredibly dense structure. Second, a high temperature of 400 degrees Fahrenheit. That's 200 Celsius. This heat does two things. It activates the resin, causing it to polymerize and permanently glue the fibers into a single solid block. And at the same time, it evaporates any remaining moisture, which escapes from the board as hissing steam. After a few minutes in this steel embrace, the fluffy mat transforms into a hard, dense, perfectly flat, and still very hot board of medium density fiberboard. After the press, the hot boards can't just be stacked. They need to be cooled to relieve internal stresses. They're placed in a special fan cooler, which looks like a giant filing cabinet, where they slowly cool while being fanned with air. Once the boards have cooled, it's time to give them a finished look. First, they're stacked in high piles and left to rest for a few days. This stabilizes their internal structure. Then, each board goes through a sanding machine. Imagine a giant belt sander with several heads. Wide abrasive belts remove a thin surface layer from both sides, bringing the board to a perfectly precise thickness, for example, 16 or 18 millimeters, and creating that famous smooth as paper surface. And the final touch, cutting. Huge saws cut the large industrial boards into standard commercial formats. After this, each batch goes through strict quality control. Its density, strength, thickness, and surface quality are checked. The finished, perfectly smooth boards are labeled, packaged, and sent to furniture factories, where they will become the foundation for elegant and stylish items in our homes, silently demonstrating the noble path that ordinary wood dust can travel. The global market for medium-density fiberboard is a giant machine that turns over more than $25 billion a year. And this machine has no plans of stopping. Forecasts say it will grow by 6% every year. That means the demand for this smooth material is just insane. So who's the head chef in this kitchen? The undisputed king is China. It produces over 50% of all the medium-density fiberboard in the world. But Europe is no slouch either, with powerful players like Germany, Poland, and Turkey producing millions of cubic meters of high-quality board. Now for the volume. Every year, about 100 million cubic meters of medium-density fiberboard are produced worldwide. That number is so huge, it's impossible to imagine. Let's try. Picture a road. If you took all that medium-density fiberboard and built a road 10 meters wide and 25 centimeters thick, you could wrap that road around our entire planet at the equator every single year. It's an endless stream of material being turned into furniture, doors, and panels for our homes. Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress, and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter, where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These three ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyères, air heated to a scorching 2,200 degrees. Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 calories, 1,530 nanometers. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 nanometers, 1/200 nanometers. Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the River of Fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key, or barometer, of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces.